Welcome to Hartman Math. Today we're going to take a look at geometric sequences and series. Before we get there, go ahead and pause the video here, work through the 3 warm-up problems. Alright, number 1, a sub 200 is equal to first term plus 200 minus 1 times d. You get 1,389. Number 2, find the sum. So S sub 36 is equal to 36 over 2 times first term. Plug in a 1. You get 3 minus 40, so negative 37. Plus last term, plug in a 36. So 3 times 36 minus 40, whatever that comes out to be. 68. And that's going to equal 558 for our sum. And lastly, number 3, evaluate. We got an arithmetic series here. It's going up by 5 each time. So we got that, we know that. And the problem is we don't know how many terms we're adding up. So we're going to have to figure that out. So 309 is equal to negative 1 plus n minus 1 times our d is 5. That's going to lead us to n is equal to 63. Now we'll do s sub 63. We had the first, we had the last, so once we knew n, pretty easy, 9,702. This is lesson 9.3, geometric sequences and series. So a geometric sequence is one in which the pattern is multiplication, or division, which is essentially the same thing as multiplication. So if it's multiplying by 3 each time, that's going to be geometric. The way that we find the common ratio, which is what was multiplied each time, is to take one of the terms and divide by the one before it. Not after, before it. Take the 8th one, divide by the 7th one, and we get the common ratio. All right. Find a formula for the nth term of a geometric sequence whose common ratio is negative 3 and whose first term is 5. Here is our formula right there. Because of our sequence, if we looked at it before as first term a sub 1, now multiply that by r, multiply that by another r, so it's r squared, multiply that by another r. So it turns out a sub 1 multiplied by a bunch of r's with just one less r than our position. So that's essentially our formula right there. So we've got a sub 1. We've got r, a sub 1, got that backwards, a sub 1, we've got r, use parentheses, and no, we cannot multiply those together because it's not negative 3, it's a bunch of negative 3's, this is one single 5, so keep them separate. The only time you can do anything is if these were the same number. And then you got to be careful because you got to really know your exponent properties to be able to pull that off. All right, checkpoint, use that formula, a sub 1 equal, or a sub r, n equals a sub 1 times r to the n minus 1. Find the 13th term, pause it here. All right, we've got our 6th term. So a sub 6 is equal to a sub 1 times our common ratio to the 6 minus 1, and we know that is negative 4. That's going to allow us to solve for a sub 1 because we're just going to divide by this number. And we get the decimal 0.125, equivalent to 1/8 if you love fractions. So if we're trying to find the 13th term, the 13th is the first times the common ratio times n minus 1. So 13 minus 1 would be to the 12th power. Parentheses there, very important. 512. Example number 4, find the nth term. If we don't know a sub 1, we don't know r, so kind of the same thing as that last lesson, create a system of equations when we have 2 unknowns. So each term generates an equation. I do like to go with the furthest term down the line first, so the 8th term. But there's also another way we could do this. You can do it with the system, or you can try to relate the terms to each other. And say the fifth term, if I multiply by 3 more r's, I'm going to get to the 8th term. So if we kind of look at that, 5th, 6th, 7th, and 8th. If I multiply by an r, I get to the 6th, another one, and another one. So if I multiply by r cubed, notice that that exponent is the difference between our n values, our positions. So if we look at it that way, now we can replace a sub 8 with 24 and a sub 5 with 648. We can solve it. Divide both sides by 648. Reduce it. How do we get rid of the exponent? Cube root both sides. So we're going to get r equals 1/3. Now at this point we don't know a sub 1, so use one of these terms to do that. So if we use the fifth term, is the first term times r to the 5 minus 1 power is equal to 648. Yeah, we could divide by this. I think it's easier though, with this being the fraction. How about we just multiply by the reciprocal? Include the power. So a sub 1 would be 648 times 3 to the 4th power. We get 52,488. Finish the problem. A sub n equals a sub 1 times r to the n minus 1. All right. The sum of a finite geometric sequence looks like this. They have it like this. I prefer like this, especially for calculator use. I think it's more handy to understand. Above and below fraction bars act as if they are in their own set of parentheses. Calculator-friendly version. Some of the first n things we need to know. First term and r. We don't need to know the last term this time. We just need to know how many things. So first term, r, and how many things are we adding? So find the sum, okay? Sigma notation. So here's how we would know that this is geometric, as opposed to last time being arithmetic. If your a sub n right here looks like an mx plus b situation, like 5n plus 2, that would be arithmetic. If it looks exponential, a times b to the power of x, something like that. If it's exponential, that's geometric. So we know this one's geometric. And the base, that's our common ratio. If you're unsure, you can go ahead and plug in a 1, plug in a 2, plug in a 3 until you can see the pattern. But it is geometric. So, our formula, first term, plug in a 1. So we get negative 1/3 to the first is negative 1/3. Multiplied by 54 is negative 18. Times 1 minus, be very careful here, okay? Negative 1/3 to the power of 5. As I said, be very careful here. If this is even and odd, it changes the fact whether you should say that that just becomes plus. In general, with an exponent, don't do that. Here it's fine, there's no exponent. This is 1 plus 1/3. Evaluate this first. Use the order of operation. You would get negative 1 over 243. 1 minus negative. This one does become plus up here. But if this had been even, it would not become plus. So watch out. Okay. So if we're going to get exact values here, we did say 1 plus 1 over 243, 243 over 243, plus 1 over 243, being able to add those together, we get 244 over 243. This is 3/3 plus 1/3 is 4/3. So instead of dividing by 4/3, we could multiply by its reciprocal. A 3 will cancel here and here. A 4 will cancel here and here. And we got our final answer. If it didn't say that we could round, it needs to be exact. It needs to be a fraction. All right, part B. Let's take a look at this one. We also know this one is a times b to the power of x. So as an exponential a sub n here, we know it's geometric. So we use our geometric formula. Plug in a 1. 1 minus 1 is 0. Negative 2 to the 0 power is 1. 1 times 3 is 3. Okay. And as we said before, negative 2 to the 10th power is going to be a positive number. So this becomes 1 minus that positive number. Now we don't have fractions here, so you could use calculator to kind of help yourself simplify this. Be very careful with the parentheses. You should get negative 1023. If you didn't, try it again until you do. Example 6, find the sum. Another one where we don't know how many things that we have. So we'll use the last one as our clue to get us going and write the equation for the last one. 1458 is equal to, first, so we go back to the a sub n, 2 times the r, which we can see is the pattern is being multiplied by 3, times 3 to the power of n minus 1. We're going to solve that. It's an exponential equation. We're going to divide both sides by 2. Now, we could guess and check this, or we could use logarithms. Undo it by rewriting this as a log equation. Move the base to the other side. We get n minus 1 equals log base 3 of 729. And then you can use your calculator in your change of base formula, unless you have a super sophisticated calculator that has that feature that you can do it. But on a regular calculator, we just do log 729, divide by log 3. We're going to find out that that was 6. Add 1 to both sides, we get n equals 7. So s sub 7 is first term times 1 minus 3 to the power of 7 divided by 1 minus 3. If we use the parentheses, if we didn't have the fractions, we should be good. 2186. Now, it turns out, we talked about this in the last lesson, if it was arithmetic, sum had to be finite for us to do it. But for infinite, for geometric, we might be able to do an infinite sum that goes on forever and ever. Might be able to do. The condition is right here. In order to be able to do that, the absolute value of your common ratio has to be less than 1. If it's not, the formula doesn't even apply. Okay? So if we remember, the other one was s sub n is equal to a sub 1 times 1 minus r to the power of n divided by 1 minus r. What I want to kind of look at is this term right there. So remember, our absolute value of r has to be less than 1. So let's see, what can we come up with just as an example of an r that would fit that description? Maybe like 0.7, something like that. So what I want to do is explore 0.7 to n. And if it's going on forever, it means that n gets really, really large. So try this on a calculator. Do 0.7 to the 100th power. What do you get? Now do 0.7 to the millionth power. What do you get? Now do 0.7 to the power of 1 followed by 30 zeros. That's a big number. You're going to see that your answer starts getting smaller and smaller and smaller and closer and closer and closer to 0. So essentially when n goes to infinity, it becomes 0. That's kind of a calculus concept of limits. But it essentially becomes 0, which means this part disappears from the formula. 1 minus 0 is 1 times a sub 1. So that leaves us here. If it qualifies, this is our infinite. So if it just says s, add up all of the terms. It's the first term divided by 1 minus the common ratio. Example number 7, find the sum. How do we know that it's infinite? It's got the infinity symbol as our upper limit of summation. And we know it's geometric because it's a times r to the power of n minus 1. Will this one work? I think so. Here's our r, the absolute value 5/7 is 5/7, and that's less than 1. So we can do, the formula will work for us here. So the sum of all the terms is going to be a sub 1 goes on top, so plug in a 1 to get a sub 1. So we get 0 as our exponent, 5/7 to the power of 0 is 0, times 6, we get 6, divided by 1 minus 5/7. I think this is 2/7. 6 divided by 2/7 is the same as 6 times 7 over 2. Okay, we get 21. All right, checkpoint. Go ahead and find the sum. It's infinite. Pause here. All right, so if you use the formula, you would get, plug in a 1, you would get 2 to the first power is 2 times 3 is 6. Divided by 1 minus r is 2, so we would get negative 6. Did you get negative 6? Let's see. Let's explore what the sum would look like. Plug in a 1. 3 times 2 to the first power. That's a 6. Plus, plug in a 2. 3 times 2 squared. 2 squared is 4 times 3 is 12. Plug in a 3. You get 24. Plug in a 4, you get 48, plus, dot, 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 keeps going forever and ever. Is it possible that 6 plus 12 plus 24 plus 48, all forever, is going to end up having a sum of negative 6? I don't think so. We can't add up a bunch of positive numbers and get a negative number. So what happened? That happened. If our r is 2, and the absolute value of that is 2, is that less than 1? It is not. This one does not have a sum. It does not converge. It does not have a sum because our r value did not qualify. Next problem, let's go ahead and see if we can find the r value for which the sum, the infinite sum, would be 20. So 20 equals a sub 1, let's see, what is a sub 1? Plug in a 1, we get 0. R to the 0 is 1, times 8 is 8, so 8 is our a sub 1, that's on top, over 1 minus r. Multiply both sides by 1 minus r, divide by 20, add r, subtract that, and get r is 3/5, or 0.6. That would qualify. And then the last couple lessons I've been promising we would get to this. How do we take a repeating decimal and turn it into the appropriate fraction? So notice, here's our repeat. 2, 3, 2, 3, 2, 3. So what we want to do is we're going to start by taking this and separating it out into the non-repeating part and the repeating part. So we have 1.5 plus 0.02323 and so on. And we can break up that repeating part to be 0.023, 0.0023, 0.0000023, and so on. And what happens is the repeating part is a geometric sum. Something, this multiplied by something is that, and so on. So to find that r value, take one of the terms, divide by the one before it. So take this number, divide by this number. You're going to get the ratio. And we could write that with sigma notation. So we've got the non-repeating part plus a sub 1. So if we do our a sub n, a sub 1, 0.023 times r, which we just found out by doing the division, to the power of n minus 1. There's our sigma notation. Now we can calculate that sum. Still got the 1.5 over here, but this is a sub 1, 0.023, divided by 1 minus r. So 0.023 divided by 0.99. That's how I turned that one into a fraction, because we are trying to get to a fraction. We knew that one is a fraction. Now I think I want to decimal bust this. So I'm essentially multiplying everything by top and bottom by 1,000, because I want to slide it 3 places, because I don't want any more decimals within the fractions. So if I slide this one 3 places, I got to slide this one 1, 2, and 1 more, creating a 0 there. So this is 23 over 990. And then if we need a common denominator, we can figure out what we multiply 2 by to get 990. We got that fraction. Add them together, and then reduce it, and we've got our answer. Then go ahead and check on your calculator. Do that number, divide by that number. Is that the pattern that you see for your decimal? That's it for today. I'll see you next time.